Hi, everyone. Thanks for attending Daniel and I's session on SQL Server big data clusters. I'll be presenting first a high-level overview of how we got to big data clusters, and then a little bit more on what are the components of it, what's the general overview, and then I'll hand it off to Daniel for an in-depth demo of all the functionality that we have. Hope you enjoy it, and thanks for watching. Let's get into the overview of big data clusters, how it came to be, and then the different pieces that exist inside it. So big data clusters is really focused around data at scale. What I mean by this is that in today's world, we have so many more data sources and much larger data volumes. And all of these things are growing exponentially. So in 2016, there was actually a study that says there are 16.1 zettabytes of data being created each year. And in 2025, we're going to see that number balloon almost 10 times to 162 zettabytes of data per year. And with this massive growth, you really need a platform that helps you handle such a large amount of data. And there's a lot of reasons why all of this is happening. We have a lot more sensor data, we have a lot more camera data, and then we have just the general buildup of data over time that all organizations now want to be able to extract insights off of. And there's a lot of enhancements technologically that have allowed us to improve this process and kind of help better extract insights from this data, whether you're at the data scientist level or you're at the business user level. Everyone just wants to get information quickly and efficiently out of all of the data that they've collected in their system. So there's a few things that have happened that have enabled this. We've seen a lot of advances in compute optimization. We've seen technology like data virtualization come up, which allows us to basically bring in the data that you have in other data sources into a single one. So for example, SQL Server allows you to virtualize data from all sources such as Oracle, MongoDB, you name it. And so in addition to this, we've also just seen general optimizations and innovations around things like storage and processing. So these things have just become cheaper. And so with all of these advancements and knowing how data has increased in both volume and in the number of sources, we decided to create big data clusters. And leveraging all of these enhancements that you see on the slide, we're able to help you extract and get the most out of all the data that you've collected. So with all of these data sources and these technological advances, once you have this data in today's world, you can actually start getting insights out of it. So as an organization, you have a whole lot of options now of how to use data to make your organization better. So I'm actually going to go through a few examples. So use cases where BDC can be used and big data in general can be used to help you and your organization be more proactive or better about running the organization and the day-to-day activities. So the first one to start off with is the healthcare industry. As we're seeing today, understanding and being able to predict the resources that you need, the resources that are going to be used, et cetera, is really important. So let's say you are a hospital and you need to understand, do I have enough beds? Do I have enough medication for my patients? That's something that you can use big data for. You can extract these insights. You can understand maybe how long are my patients going to be in the hospital? How many beds do I need because of that? And then even more information from that. You can do things like understand also how are your patients interacting with the hospital, whether that's in and out of the hospital. So whether you're trying to understand how are they eating, how are they exercising, being able to understand and collect all of this data is incredibly important. Secondly, we have the financial industry, which is similar to the healthcare industry. So that's another place where big data can really help you identify and predict certain things. So let's say, for example, you're a bank and you want to understand whether or not a new client is risky or whether or not your customers have fraudulent charges going against their accounts. You can use big data to understand these things. You can also use this data to do a whole lot of other things like maybe chatbots or in general just other risk management activities. And to that point, big data clusters is a platform that can help you do that. And then lastly, we have the government. And this is an industry where it's incredibly highly regulated. Maybe you don't want to move your data to the cloud. And so you really need an on-premises or hybrid cloud solution that lets you extract a lot of the data that you've now collected. So this could be things like emergency preparedness or revenue prediction or even understanding the environmental impact of certain projects. Maybe the government is building a highway and they need to understand how it's going to affect civilians and the environment. And with all the right tools, you can start to do this and start to really understand the consequences of your actions. So with all these new analytic applications, there are a lot of requirements that come up around scale. And so what I mean by that is, how do you actually leverage the data that you've collected and stored inside your system and do that in a performant way? And so we've been building big data clusters. We've actually seen a lot of these requirements come into play, and so we wanted to address them. So there's requirements from the platform perspective, which is the underlying infrastructure and the technology being used. And then there's the data requirements. So how do you actually process all these things? And then how do you make it work for you and not you working for the tool itself? And so what we mean by that is that we abstract away things like storage issues, networking, security, isolation, all those integration points to make sure that you can have the right people access and use your data with as minimal friction as possible. So from a data scale perspective, this is where you really need to be able to do things in an efficient way. So if you have gigabytes of data or petabytes or terabytes, then you need to be able to interact with that data in a secure and highly performant way. And so we have things like an HTAP processing system, we have the compute over storage ability, and we have just in general a lot of integration around security and management and monitoring to help you really make sure that the system is performing the way you need it to. So you may be asking, how do we do all of this? Big data clusters is built on top of Kubernetes. One of the reasons why we chose Kubernetes is because in any of these environments, whether you're on premises, in the hybrid cloud, or just purely in the cloud, you really need that ability to scale. And so what we wanted to do is to give customers the best choice to help them do exactly that. So now not only can you scale up a SQL Server like you traditionally could, you can also scale it out alongside the other technologies that we've placed inside the big data clusters. So whether you're familiar with Kubernetes or not, we'll quickly do an overview of what it is. And Kubernetes is built on top of the notion of containers. So containers basically let you standardize your software and put them into a little bundle, and then you can ship that and deploy it as you need. And Kubernetes is there to help you orchestrate all of these different containers. For example, here on the right, you can see one of the Kubernetes pods that we have inside big data clusters, which is our storage pool pod. A concept we'll go over later, but it's effectively a pod that contains a few different technologies like Spark, SQL Server, and HDFS all running together. So all these technologies are localized and put together in one unit so that we can kind of take advantage of their proximity to each other. So this storage pool pod is, and in general containers, they allow us to do things like make it really easy to deploy BDC, to manage all these different containers, manage the different, the storage or compute power you need. And just in general, containers really help you make your deployment as flexible as possible, no matter where it is or no matter how many resources you need. Now that we've covered what big data clusters is actually built on top of, let's actually go a little bit deeper into what the key components of big data clusters are. The thing to remember here is that SQL Server big data clusters really is just another feature of SQL Server. So you can still do all the things that you know and love about and with SQL Server, but now with this extra punch. So we have a few key components in the big data cluster, and the first one is the controller. The controller is what we use to manage the system, whether it's configurations, whether it's managing the different pods that we have, or just any other management activity. It's all dealt with by the controller. Then we have the SQL Server master instance. And just like I was saying, big data clusters is just another feature of SQL Server. And so the master instance is actually in and of itself a SQL Server. And this is where you can connect. So for example, you can go into your favorite tool, whether it's SSMS or Azure Data Studio, and you can use and play with the SQL Server just as you would on a regular basis. You could also, for example, hook up any Power BI reports to this, and any data that's in the master instance you could see as a report in Power BI. You could also do the regular things, like you can query the master instance and still see the same results as you usually would. Like I'm saying, it's an entirely fully functional SQL Server, and it's intended to be used that way. The next two pieces that we have are the compute pool and the data pool. So these two pools are basically just a combination of different technologies and basically a couple pods put together to offer some added value to users. So the compute pool is there basically to help you have a little bit more processing and computation power when you have maybe a more resource-heavy query. And then on the flip side, we have the data pool, which is there almost as a data persistence / caching layer for all of that hot data that you're bringing into the system. To continue, we have the storage pool, which is really the bread and butter behind big data clusters and what makes it great. So inside the storage pool, as we showed on the previous slide, we have a few key components. We have SQL Server, we have Spark, and then we have HDFS. And so the storage pool is really where you can leverage the best two compute engines, SQL and Spark, to help you get the most out of the data that you have. And so all of this is stored in the shared HDFS as a storage layer. And this is what basically allows you to have any data, whether it's relational or non-relational, available to you and your organization. Then lastly, we have the application pool. So this is where you can take all the insights you've created, maybe any artifacts, let's say a model that you've produced from the data inside your master instance or inside the storage pool, and deploy that for an end-facing user. So what I mean by that is, let's say your data scientist has looked at all the data, they've created a machine learning model out of it, and now they want to expose that model so that anyone can use it. So the data scientist or the data engineer can actually go in and take that model and deploy it on the application pool, and now that's available either as the application in and of itself or as a REST API for use from anyone, whether that's internally or externally, however you see fit. So to summarize, there's just a few key components of the big data cluster: the controller, the master instance, the compute, data, and storage pool, and then the application pool. And all of these have slightly different use cases, but they effectively allow you to do whatever you need in the best way possible. Now that we've covered the key components of big data clusters, I'm going to actually show you an example of how these different components can be used and why they're important to different people. So let's take this example of a healthcare scenario. We're actually going to be predicting how long a patient is going to be in a hospital. So there's a few key personas here, namely the IT administrator, we have our data scientist, we have our frontline care worker, maybe a doctor or nurse, and then we have our top line user. Maybe this is actually someone who runs the hospital or helps manage all the day-to-day operations. So let's start first with the IT administrator. So this is someone who's going to set up the big data cluster and really needs to understand the needs of the system and the operations that are going to take place from a technological basis. So this is a person who would set it up. Maybe they're the person who would scale it if needed. And then they're also going to be the person that understands, okay, if we're getting a lot more demand or usage today or this week or this month at the hospital, then how are we going to pivot the system to handle that accordingly? And so using the Kubernetes technology that we talked about earlier, they're able to maybe measure and scale out the system as needed. Then we have the data scientist. So this is someone who is there to really help the hospital understand and act on some top-line goals. So for example, this could be something like helping the hospital understand how many patients are coming into the hospital, maybe at what frequency, how long are these patients staying, are there any commonalities between the patients that are coming into the hospital, and what are the resources that the hospital needs to provide the best care to them. So the data scientist has a few ways to interact with the big data cluster. They could interact with the master instance, they could interact with the storage pool, they could interact with the application pool, all for different reasons. Primarily with the master instance and the storage pool, the data scientist is trying to get and use the data that's in the system. And so this is where we don't want the data scientists pulling information onto their own computer. We want them using the resources that the big data cluster has to analyze the information and create insights off of it. So maybe there's a lot of relational data inside the master instance, and maybe there's some unstructured data like images, or maybe just some free speech between the patient and the doctor, and they want to analyze all of that. So they can do that by connecting to each of those parts, using that data, and then maybe in the end generating a model for it. So let's say the data scientist has the goal of figuring out how long a certain patient would be in the hospital. Then they can use all the data that's in the system, create a model that can predict that, and then expose that for later use. And so, like we mentioned earlier, in order to do that, they could use the application pool. So they could either themselves, or by handing off the model to a data engineer, they could create a application or a REST API to expose that model so that someone else or another tool could use it. And they would do that using the application pool. Then the next person is maybe this front care line worker. So this could either be your doctor or your nurse, or someone who's just really on the ground trying to help patients. So like we mentioned earlier, maybe the data scientist has created some models to help everyone understand how long a particular patient could be in the hospital, and the care line worker is going to be the person that uses that application or that model. So as a care line worker, maybe I go to the web application that my IT team has set up, and then I can see information like when I check in a new patient, I can see based on the information they've given me and their past health and what they're inflicted with today, we can figure out whether or not they have or whether or not they're going to be in the hospital for 2 days or for 15 days. And you can imagine this being really important in scenarios where maybe we need to understand how long the patient is going to be staying there. That way they can be situated in a different ward. So if there's one area of the hospital that's a little more dynamic and needs a little bit more space or room, then we wouldn't put a patient that's going to be in the hospital for a while in this area. And then lastly, we have maybe the business analyst or your chief medical officer, or someone who's more at a larger and higher scale than your regular nurse or doctor who's paying more attention to the actual patients themselves. So this person may be interested in still the length of stay of patients, but maybe at a higher level. So they want to know how long are all of the patients going to be in the hospital as opposed to just the singular one that they're caring for. And so these people are going to interact with the master instance. They can have their Power BI reports, have queries set up against master instance with all that information. We could have the data scientist actually put a model inside SQL Server so that every single time a patient is checked in, it generates their length of stay, and this business user can go ahead and see all of that, and they can use that to create and help guide their decisions. So just to make this a little bit more concrete, let's take a look at some sample Power BI reports that could maybe come out of all the work that the different people have done in the organization. So on the screen, we can see a report that a care line manager may see. So this, like we said earlier, could be a nurse or a physician of any type, someone who's just on the ground of the hospital taking care of patients. So these are people who may be more interested in individual patients and want to understand a lot of information, maybe like the capacity of the hospital, how many people are checked in, maybe particular patient information like we see on the bottom left. So what are their levels, how many days have they been in the hospital, how many days do they have left, etc. And we can also see information like what's the predicted discharge day for patients. So all this information might be incredibly useful for a nurse or doctor who's trying to understand, how many days or what days are most important at the hospital. So for example, we can see Monday and Tuesday, there's going to be a lot of patients discharged that day. So maybe they know that they are going to need a lot of help that day, or that they should make sure that they're, very efficient and on time. As opposed to maybe Friday or Saturday where things may be a little slower and they may have a little less patients coming in or checking out. And so using this information, you could imagine how a doctor and nurse could, improve their day-to-day operations and activity by just even understanding how much work they have to do or which patients need the most help or care on a particular day. Then we have the report for the chief medical officer of the hospital. So this is someone who's going to be very high level. They're just looking at the general trends of the hospital, trying to understand, how is the hospital operating and at what rates. So we can see information like we saw in the previous report, like total capacity, the patient total once again. But we see more information like what's our average daily admission rate, what capacity are we operating at, etc. And so, like I said, this person is more interested in these high level trends. And so using the information that either the data scientist has collected or any of the other people as part of the organization, he or she can actually go in and make decisions based off this information. So you could imagine them saying something like, hey, we have a lot of patients this week coming in with some particular symptom, maybe it's flu season. So we're going to need a lot more saline, or we're going to need some more flu vaccines, etc. And so he can take this information and use that to make decisions such as what resources that we need to order, or how many more beds we may need, etc. So this really shows you how all the different pieces of the big data cluster work together, and how the different users come together to basically help the patient get the best care possible.
Thank you, Rahul. I'm Daniel Coelho, and I'm a senior program manager with the SQL Server Big Data Clusters team. In order to provide a solid understanding of the capabilities of the platform, let's walk through a complete end-to-end scenario. I've deployed big data clusters on a Linux workstation under my desk using Azure Data Studio. It's very easy to do. You can also use AZ Data to configure additional deployment profiles and tweak the cluster to fit your needs, even for sandboxing. Just like the scenario that Rahul described, a real estate agency scenario would benefit from the same surface capabilities that BDC provides. The flexibility of the platform allows those concepts to be easily interchangeable and be applied across many verticals use cases. So this demo scenario is about machine learning application development. Our synthetic real estate agency is heavily invested on SQL Server and Power BI, very common. And they just hired a data scientist and data engineers to augment their current systems with machine learning. So the focus is to provide that competitive advantage to our real estate agents.
Let's get started with the demo. We are here using Azure Data Studio as our interface to work with the SQL Big Data clusters. It is connected to my BDC cluster that runs on a plain vanilla Kubernetes server. You can use these management dashboards to check status of other services running on the cluster, create and open new notebooks, and perform both management tasks and development tasks. As expected, you can here on the left navigate database objects, server objects, and HDFS objects. And this one we're gonna use to load data into the storage pool. One of the greatest features of ADS is its Jupyter Notebook interface. It serves the DBA, the data engineer, and the data scientist. And it does this by supporting multiple kernels, as you can see here. For this notebook in particular, we are using the PySpark kernel, but you have a SQL kernel and all the other kernels at your disposal. Throughout this demo, I'm gonna play different roles, and I'll start as the data scientist just hired to solve this house market value prediction solution. The DBA then created a database for me to use, right here, and the data engineer told me that I can begin my analysis just using the CSV file that he provided me. I've previously loaded this file into HDFS in a sandbox space right here. So now that everything is in place, let's move on. The scenario objective is to create a solution to help our real estate agents to price houses efficiently. I'm gonna hide this connection tab here. I'm gonna focus on the notebook. We're gonna use the Boston housing dataset, but our focus is not much on the model itself, and the use case itself is more understanding the workflow of building an end-to-end solution using big data clusters. So this data set gives us the possibility to tackle this following usage patterns, like quick ingestion, as I shown, loading data into the HDFS. It's a small file in this case, but it can scale to big data easily, and that's where the power of Spark relies. We're going to demonstrate some of the virtualization capabilities. We're going to demonstrate, of course, Spark for data engineering and data science tasks. And we're going to use Kubernetes, MLflow, and Onyx, and SQL Server to patterns that could be generalized to a greater number of use cases. So you can get this sample notebook and apply, of course, with different data and different models towards a lot of other use cases. Let's get a Spark session for us to work with. The first step we're going to focus is on ingesting data. We uploaded the data set there. As you can hear, the Spark session is loaded. And now it's like business as usual for Spark. We're going to define the variable here just to hold the location. You can assume there's a HDFS prefix here, and then we're going to read the data frame with Spark. And this is business as usual for Spark. And then you do the initial data preps, print schemas, and you move on and on and on. But for now, let's focus on some of the data virtualization considerations. Data engineers just might use different strategies to grant you access to that data. He gave me a CSV, but in a corporate strategy, of course, the flexibility of getting a CSV is very important for analysis, but in a corporate strategy, probably he might have traveled different roles to grant access to the data for you. He could have just virtualized a table for you on SQL Server. This table could be a simple table under SQL Server master instance. It could be a data pool table designed for big data, like sharded data sets. Could be a totally virtualized external table module, like referencing external databases such as Oracle, MongoDB, Teradata, generic ODBC data sources. Or it could be even a storage pool virtualized table, like actual tables pointing on top of files on HDFS. As a data science using Spark for us, it doesn't matter. We should use Spark methods for reading those objects. But in this use case, we're gonna just demonstrate how a data engineer would virtualize housing this CSV that I just uploaded into the SQL Server database. We're gonna use this Apache Spark connector for SQL Server and Azure SQL, which is an optimized connector that communicates perfectly in a distributed fashion with the SQL Server instance. We're going to copy data to both SQL Server tables, one master on the master instance and one in the data pool. Let's take a good look at them using a SQL notebook, which is an awesome feature for Azure Data Studio. And then we'll read it back to a Spark data frame just to demonstrate the capability before we start modeling. Now let's change hats to the data engineer. So the data engineer is going to read that data set using the same patterns that the data scientist used to read them. And he's going to have a Spark session of his own. And then he's going to use the Apache Spark connector for SQL Server and Azure SQL to create those tables within the SQL Server instance. This is the connector type. There's a special class that knows how to connect in the best way possible to the SQL Server engine. It supports Azure Active Directory integration, so all the benefits of having an AD enable connection apply. Then we can use a standard Spark patterns to write the data out or across. So we're gonna get the same house DF here. I'm gonna write using that connector to a table named house. Now here we are writing is basically the same writing pattern, but we are writing to a data pool table, which is a sharded version designed towards like more big data centric use cases. So once we are done, We're going to use a different notebook here just to validate. This is a SQL notebook. So let's focus on the connection here. So let's take a look. Here we are connected to the Microsoft SQL Server big data clusters. And let's take a look if the table has loaded. As you can see, the notebook already tells us that the data is there. This is the SQL Server master instance table. And over here, you can see the data pool based table. We're using a count big function, which is a very useful function for big database tables. Now let's close this notebook here because we're not data engineers anymore. And we're gonna go back to the data scientist notebook, exchanging hats again. Now just for the sake of validation, we're not gonna actually use this data frame, but just for example's sake, let's read the data from the data pool table into this specific data frame. Here's the notebook running, and we get the same 506 lines. Now let's focus on the modeling side of things. We're going to use PySpark, standard Spark ML, and MLflow to actually go with the training. Here's a standard data analysis, like taking a look at the correlation between the variables. We're not going to focus too much on that. I just wanted to point that if you print, where are we, you can see that we are within actually a directory under one of the containers on the Kubernetes cluster. We're not working on the local machine. The notebook is attached to the cluster. From this point on is basically using MLflow. We have a tracking server running to track all the experimentation that was done. I'm not going to rerun all the cells, but basically you can point to a corporate tracking server, a corporate established MLflow solution to to focus all your experiments, images, and models and pipelines. This was mostly done as an example, but we use MLflow to track all our model experimentation here. So the MLflow library was loaded within the cluster successfully. We created an experiment name called real estate market val, created an experiment ID, and then we moved on. This is a simple vectorization, split the data set, and then we use the standard MLflow run to go and log the parameters, set some tags, and basically build the models using Spark ML. So we have the first model, which is a linear regression model. The train R squared, around 74% of the variance explained. This is a very bad RMSE, it's a very small data set, but it's doing its job. With a bigger data set, a bit more modeling, we would get better models. So we created the first model, a little worse on the test data set, which is expected. We get a baseline here. Took a look at the residuals. This is data science as usual. Then we train a couple of different models. We train the GPT regressor, and then we train the decision tree. One cell that I like to point out is, you can get exactly the environment that's being generated as you move on, the dependency on Python, the dependency on PySpark, and an MLflow. The decision tree regressor gives us feature importance, which is always good. And here is a print screen of the MLflow tracking server with all the experimentation done for these models. And then from this, we can decide which model is best for us before we move on and operationalize and validate the model. Now that we have some models built, let's get those models and make them useful for our application developers. When you talk about training modeling with Spark, you have this non-exhaustive list of options to operationalize that model. And this is one of the common patterns that we have. So the first one is to convert the model, Spark ML model, into an mLib bundle, which is a portable package format. And we're going to operationalize within SQL Server using the Java language extension. So the scoring would happen within the SQL Server instance. This is very good for low latency or scenarios where you have data dependencies that rely within the SQL Server database. We could also have used MLflow Spark and standard Spark serialization to create an application, but that application would be Spark context dependent. So we would need PySpark and a Spark backend to run. There are very good scenarios where you want this. So mainly applications that maybe rely on Spark streaming or rely on actual big data for batch inferencing. Our use case is more simple, and we just want to convert that data into another very common packaged format for models called ONNX. And we're going to generate a binary ONNX file out of our Spark ML model. From that point on, our model is not going to be dependent on Spark anymore. It's a portable format. And then we're going to use the Kubernetes app deploy from BDC to serve the model as a REST API. So our example assumes no data dependency. It's just a standard model. We're going to retrain it eventually as new data comes in. And it kind of requires REST API compatibility. So we focus on ONNX and app deploy. So in this final cells, we're going to use MLflow ONNX and ONNX tools to convert the Spark ML model into the portable format. This line does the job. We're going to save the model into MLflow just for tracking. And then we're going to use the fwrite function to serialize the model to disk. When we save the model to disk, it creates a specification for deployment that we're going to leverage further to app deploy. It creates a specification. I created a scoring function. It's a simple function to load the model and score it. And of course the requirements for the Python virtual env with all the libraries it relies on. You can see that the PySpark dependency is gone. I created an ONNX local inferencing test just to test that scoring function. Basically the same code. Load the ONNX runtime, load NumPy, load the model here, generate some data as the inputs, and then we do the session run, which is the inferencing session, and we get a scoring result for the model. Now that we have a portable model working, validated, let's get to app deploy. I previously created the deployment profile based on that specification that I showed before, using Azure Data, which is the primary tool to manage and interface with the big data clusters. It created the application, and the application was waiting for creation. Let's validate if the application is now ready. It is. So now you can use the command line to test the application, sending inputs and getting the prediction. Success. The results don't make sense, but that's not the point. And finally, you can describe the application. So you can give the Swagger API description to your developers so he can move on and integrate the application with the final application. So let's take a look at the Swagger description. Let's take a look at it at the Swagger editor. It's going to convert automatically from JSON to YAML. And here it is, the endpoint MV predict QA ready to be integrated into the application. With that, we reached the end of the demo. Let's go back to the presentation to take the learnings and summarize.
What have you learned? Hopefully a lot. Rahul and I covered a lot of surface, and we do encourage you to go back to this material later on. So SQL Server Big Data Clusters is a modern, comprehensive, and flexible platform to provide end-to-end analytics for many organizations. Let's go through some key takeaways from this session. So SQL Server BDC leverages what you know and need, right? What a lot of organizations are used to. So we have SQL Server T-SQL with the added scale out for compute and data. We have the Active Directory integration, the governance and compliance features most organizations rely on today. And it fits perfectly for on-premises, our most common scenario, and for both for private and hybrid cloud solutions. And then on top of that surface, you go ahead and you differentiate with both big data and machine learning. So we do provide a package, Apache Spark and HDFS deployment. So these are the de facto standards for big data engineering and big data science at scale. We are also looking at Kafka, Apache Arrow, and others for our commitment to keep the platform evolving as we move forward. In terms of data, either attach remote data sources by the means of the HDFS steering capabilities and the Polybase capabilities that we have. Also use Spark to do data ingestion and remote data querying. Move the data if necessary, if it fits your scenario. This makes it flexible to any scenario. So we do carry the baseline components to either just query remote, ingest what you need, and at scale with speed and with flexibility. Then you go ahead and you operationalize on modern standards. We have Kubernetes and DevOps at its core, and MLflow and app deployment possibilities. That's far from an exhaustive option set, because our main target with BDC is providing you the capabilities and the core components so you can build the best solution to feed your organization. Let's talk resources and moving forward. One key takeaway here is that the developer edition is free and very easy to deploy on AKS or a local Kubernetes cluster. There are a lot of resources out there, and we are listing the most important ones here for you to get started. We have a very good getting started guide, deployment guides, and some use scenarios that you can leverage. Rahul and I wish it was a valuable time spent, and we are now available for questions. Thank you very much.